Okay, in this video, we're going to classify the real numbers and find some characteristics of numbers in the real number line. So we're going to classify them, we're going to graph them on a number line, we're going to we're going to compare values of real numbers, which one's greater than, less than. We're going to find the opposite, and there we're talking about, the sign of the number there. And the absolute value of a real number. So first thing, the numbers you're used to dealing with, the ones you learned maybe in like say kindergarten, are the natural numbers. Now these are also sometimes called the counting numbers because they're the numbers you naturally start counting by. So they start with 1, 2, 3, 4, 5, and they go on to, they just keep going for every natural number. You just keep adding one to get the next one. So 6, 7, 8, etc. Whole numbers, that's really just the set of natural numbers. So let's say the set of natural numbers, let's represent it with this little symbol here, like an N with little slash there. Okay, so it's like kind of like a capital N. If you want to talk about the whole numbers, well, the whole numbers are just the natural numbers plus 0. I'm going to draw a little set notation, the little curly Scottish brackets there. So that's all the whole numbers are. The integers, they're all the whole numbers, and they're the negative whole numbers too. And of course, we don't have a negative 0, so we need to have that. But integers are they're very similar to the whole number shape. They also have these are the opposites. So negative 1 is the opposite of 1. It has the whole numbers and its opposites. And we're going to represent integers. We're not going to represent one at I. I'm just going to represent it with a Z here. You don't have to know these letters, but say you get into college and you start seeing these them represent sets of numbers like this. Sometimes you may see that way later on, but don't be creeped out by those now. When we're talking about numbers on a number line, we're graphing. Usually we might center it at any number, and we just draw a line and we label each point on there. So like here, this would be 0 on the number line, and we always put our right numbers, our positive numbers on the right, and our negative numbers going toward the left there. So that's how we're going to graph these. All right, if we want to use integers. Okay, when we're talking about integers, remember that's the positive and negative whole numbers. So just as to help you express this, all right, negative 2 is an integer. All right, and you might think, well, it's just all positive negative numbers. Well, negative 2.7, for instance, that's not an integer. So it's only the you're not going to have any like decimal. You're not going to have anything after the decimal point. So if we want to talk about the lowest Fahrenheit temperature ever recorded was 129 degrees, and actually this should be 129 degrees. They should have either Celsius or Fahrenheit here, so that's a little typo there. But you would represent this with negative 129 degrees, and it's either degrees Celsius or Fahrenheit, and that those aren't, of course, interchangeable. I would think that this temperature is probably Fahrenheit, if I had to guess. All right, the shore surrounding the Dead Sea is 1,348 feet below sea level. So we would record that with, like, if you want to kind of get a picture of this thing. So here's the sea level, and we want to go 1,348 feet below sea level. So that's going to be essentially negative 1,348 foot elevation. So if you were above sea level by 1,348, that would be positive, and we wouldn't need to put the positive sign. It's understood if you don't have a sign that it is positive. All right, when we talk about rational numbers, that's anything that can be written as, basically, when we say quotients of integers. Quotients, that's really a division problem, right? And what did we say before? Division problems are, let's write a division problem. Well, 8 divided by 2. Isn't that the same as 8 over 2? Let's see, 8 divided by 2 is 4, 8 over 2 is 4. So really, when we're saying it's written as a quotient of integers, you can just kind of think of this as it can be written as a fraction. And when we say it can be written as a fraction, we mean that it can be written as a fraction where you have to have integers in here. So we're not saying that you would have 2.7 over pi. That would not be a rational number because neither of these are integers, in fact. So, and we can't have 0 in the denominator. You can't divide by 0. So when we're talking about rational numbers, it's the set of rational numbers actually looks like this. 0 is a rational number, and then you can have, say, 1/2. You can have 1/3. You could have 1/4, and you could have 1/5. All right, but you could also you keep going as much as you want in that direction, and we'll actually kind of map this out later. We want to graph numbers on a number line. What we want to do is take all these numbers, okay, and we want to compare their sizes. Now, these are not all of them are positive, so I'm just going to put 0 at the center, and I'm going to try to kind of rank these to see. I want to know how big I need my scale to be. So this one is about. I know that's -3/2, and fractions are great, but when I'm comparing sizes, I really like mixed numbers if I want to graph it, or if I want to do it as a decimal. That helps me. This is a -0.6 repeating, so I know that's between, it's 0.6, I know that's between -1 and 0. This is going to be between -1 and -2. This is going to be right in between 1 and 2, because that's 0.5. 1 and 1/3, that's already a mixed number, so that's pretty convenient. 23 over 8. Let's see, if I do 8 into 23, I'd have 8 times 3 would give me 24. This is going to be 2 point and some change. So it's going to be 2 and 7/8 here. If you do 8 times 2 is 16, and subtract 7 there. So this is going to be 2 and 7/8. So it's going to be really, really close to 3. There's 3 and 1/4. That's already written how I'd like it. So the biggest number here, I'm not going to go above 4. So 1, 2, 3, 4. 1, 2. I'm going to go all the way down to -3, even though I don't need to go that far. So -1.5. I'm going to label that point here. -0.6. Let's see, -0.6. That's like 2/3 of the way. So it's actually kind of convenient to just leave it as a fraction. But it's 2/3 of the way toward -1. So I go halfway there, and you don't want to go halfway of halfway because that'll be 3/4. So 2/3 would be about right here. Doesn't have to be perfect. All right, and then we have -1/2, which is right between 0 and 1. So I'm sorry, it's +1/2. All right, 1 1/3 would be past 1, about 1/3 of the way. You know, if you separate this into 3 pieces, it'll be 1/3 of the way past 1. That's 1 1/3 right here. And then 23/8, it's easy. Like 23/8, I can't picture where that is. You know, have you ever seen a shoe size that's 23/8? Or actually, my shoe size. In some shoes I wear, it kind of varies. But my shoe size is 19/2. Anybody have a 19/2 shoe size? Well, you might have a 9.5 shoe size. And then some shoes it's 10, some shoes it's 10.5. Kind of varies by brand and the shape of the shoe. But just mixed numbers are easy for us to picture and compare sizes. 2 and 7/8 would be, so let me label 2, 3, 4. It would be almost all the way to 3, so you can just put it really, really close. 2, 3, but not quite there. And then 3 and 1/4 is just. I'll put this little mark to say halfway between 3 and 4, and I go halfway that halfway, and this point right here, that's gonna be 3 and 1/4. So graphing these numbers, even though fractions are great and improper fractions are great for doing calculations, so you want to multiply or divide fractions. When we're trying to picture a number, sometimes writing them in a mixed number form really helps us out. Now, irrational numbers. When we're talking about irrational numbers, we talked about rational numbers that can be written as a fraction. And again, you don't have to know this, but if ever you see this, a Q with a little line through it, that's the math people language. Remember I told you math is a foreign language? Math people sometimes like to write that, and they think at rational numbers. Now, why don't they put R for rational numbers? Well, because the symbol R, we already use that. We actually use that for real numbers. So they said, oh, well, R is taken. All right, let's see. P, Q, R, and then S. Well, let's just pick Q. Let's go right next to it. I imagine that's the logic behind that. Now, irrational numbers, they cannot be represented by points on a number line because we can't really nail down exactly what they are. You can think of pi. All right, what is pi equal to? Well, pi is actually equal to, you might say, 3.14, but pi is not equal to that. Pi is approximately 3.14. But what pi is, it's not a number we made up. It's a physical comparison of, you ever seen this equation? Your circumference is equal to pi times diameter. We'll solve this equation for pi. I'm going to divide by diameter on both sides. Pi is any circle's circumference divided by its diameter. So, and it's a number that we can get. It doesn't nail down to exactly what we'd expect it to be. It's not like a rational number. It's just a really weird physical number. Other irrational numbers are, let's say, can you take the square root of 4? Oh yeah, that's 2. So that's not irrational. That one's okay. But what about the square root of 5? There's no number, there's no really clean rational number that when you square it, raise it to the second power, you get 5. So square root of 5 is going to be this crazy, it's going to be this 2 point, and it's going to just go on forever. That's really a rational number. Now real numbers, again, I said we represent that with a little capital R with a line through it sometimes. These numbers, they actually comprise all the rational and irrational numbers, and you can see a little graph of these. We actually separate, rational numbers off here. You get the weird square roots. You got pi and the expression with pi. Those are the most common examples of irrational numbers you're going to see. You also have, over here on this side, your rational numbers, which there's this kind of subset, and these subsets containing each other. So if you're a natural number, you're all of these. Now, you're not rational. If you're a natural number, you're a whole number, an integer, and a rational number. And then, of course, you're also a real number. Real number is this is all of these together are the real number set. And then, of course, you could be a whole number. And if you're a whole number, you might be a natural number. In fact, you're always a natural number unless you're 0. Whole number is the only zero is the only whole number that is not a natural number. But this kind of shows you how you kind of break down these sets. And the reason we separate these is because some of them have nice, well-behaved properties that others might not. The biggest difference is especially between the rational numbers and irrational numbers. But we'll talk about all those. Ordering of real numbers, well, we're going to always helps to picture that number line. You got 0 here, and then you got it increases from 1 to 2. That was a mistake here, right? You don't start counting at 2 to 3, and then when you go to the negatives, it's the same scaling, but it's just you proceeding with a negative. And when we want to compare sizes, is -3 less than -1? Okay, well that already looks good. Wait, 3 is not less than 1. But it's -3. It's further on the left. So if you're going further to the left, that's less than. If you're going further to the right, that's going to be greater than. Okay, so that's a good little mnemonic to help you picture that. But it's in fact true that -3 is less than -1, even though +3 is not less than -1. All right. When we're talking about opposites, again, we're talking about the signs. So if you want to put the opposite of a number, you just put a negative in front of that number. And something to see, you see this double negative rule? The opposite of -1, let's see, the opposite of -1, well, if we want to make a number's opposite, we put a negative in front of it. But what's -1? Well, that's actually going to be +1. So the opposite of -1 would be +1. All right, so if you have these numbers, the opposite of -4 would be +4. Now, you could write the plus, but it just looks weird. It's understood. We don't put it there. So that's +4, opposite of 3. -3 is 3. Opposite of 0, well, even if you tried to put -0, it really has no value. The zeros is a unique number, since zeros and actually like that perfect center, you're not going to the other side of the line because you're in the center. See, -1 is on the opposite side of 1, but you can't be on the opposite side of the center. Let's move from the center to the other center. Well, there's only one center. So opposite of 5 would be -5. Opposite of 19 would be -19. So that's basically how that works. All right, last thing, we're talking about absolute values. I know you've seen this before, but these little signs are absolute value signs. That just means take whatever's in here and make sure the stuff inside altogether is positive. So it's what it really is. Absolute value actually is a physical representation. Instead, that's the rule for how to calculate it. But what absolute value is it's actually, you can think of it as the number's distance from 0. And the reason that we think of it that way is because distance can't be negative. A good way to think of it is like, all right, say here's Mr. Venable, and I'm here playing my TI-84 guitar, and then over here is this is Sister Larry, and she's playing her acoustic guitar, and we're playing together. And let's say the distance from me to her is 7 meters. Does that mean the distance from her to me is -7 meters? No, that wouldn't make sense. So distance is always positive. That's why absolute value is always positive. So, when we're talking about absolute value of 5, it's 5's distance uh, from 0. Same thing with here. Negative 5 is, if you go to negative 5, right? It's 1, 2, 3, 4. It takes 5 hops to get back to 0. All right, so here's the thing. These grouping signs work in the order of operations of parentheses. So you kind of do them first. So I'm going to do this first. It's going to be positive 5. Then we throw in this negative. So then this becomes negative 5. Again, this is do the grouping symbols first. This becomes 13, and then throw in the negative, and you got negative 13. 8 minus 5. Do what's in here first. Do this stuff first. Okay. And the absolute value of 3 is just 3. This one's going to be a negative 3, and this one's going to be, here's this 9. Throw in the negative, you get negative 9. Okay? That's the end of this part of the lecture. Yeah!
The views and opinions expressed in this video are solely those of Mr. Vogel and do not necessarily reflect those of the school district. Harding Marketo, its board of directors, administration, may not secretary of schools, or anyone else. Visit our website at shhkoto.org.